Hello, welcome back. So we are looking at section 3.3, Cramer's rule, and then also volume and linear transformations. So Cramer's rule says that if we have an invertible matrix A, and we have B solution, vector B as a solution for our matrix equation AX equals B, then we can figure out what our solutions are with the determinant of our matrix A with a column replaced by B divided by the determinant of matrix A. So you have like the various columns of matrix A. Let's call this I, and then like that, right? So these are all column vectors. And so the determinant of A sub I of B, so A sub I of B is going to take, is your determinant of let's see. So we take this column, the ith column of A, and replace it with B. And so this is this matrix A sub I of B. And you take the determinant of that and divide it by the determinant of your n by n matrix A, and you can get you can calculate all the solution x for this matrix equation. So there's yet another way to find your solution. So how can we use Cramer's rule to solve this system? So first we need to establish what our matrix A is, what our matrix B is, and then what our AIs of B. So work that out on your own, and pause the video, and then we will look at it together. This is weird. So we have our matrix A, which is 3, -2, -5, and 4. B is 6, 8. And then our A1 here is 6, 8, -2, 4. A2 with our column 2 replaced by B is going to be 3, -5, 6, 8. And so x1 is going to be our determinant of this, which is 24 minus -16. So that's what? 40 divided by our determinant of A, determinant of that, which is 12 minus 10, which is 2. So x1 is 20. And then we have x2. And that's going to be our determinant of this, which is 24 plus 30, which is 54 over our determinant that we already calculated of A, which is 2. So 54 over 2 is what? 25 plus 2, 27. So our solution is 20, 27. You could also solve this, the way that we had been before, where we take our augmented matrix and we do some row reduction, and so that we end up with our solution set as well. But here's yet another way to find the solution to a system. It's nice with 2x2s because the determinant's pretty straightforward. But with 3x3s and bigger, it works. It's just like it's a little more computation heavy. Long in the book, and you're seeing that we're skipping an application to engineering heading, then you're right. That is so that you can, if you so desire, you can look at that for a application project, because there are very cool applications of Cramer's rule for solving things in like engineering things, like Laplace transforms and stuff like that. So do check that out for your applications projects or for journal entries if you so desire. Alright, So, the question came up in class of, is there a formula for finding your inverse? And there absolutely is. So the formula for finding your inverse, if you don't want to, do your augmented matrix with identity matrix and then do your row reductions so that you undo using all the elementary row operations, so you build yourself an inverse matrix, you can find your inverse of a matrix by taking 1 over the determinant of your matrix and multiplying it by the adjugate. And the adjugate is a matrix of your cofactors. Remember that the cofactors that we had from the previous video is the one before in section 3.1. So our cofactor is with your negative 1 to the I plus jth power times, so changing like the sign, times your determinant of your matrix A, which has the row I and column J eliminated, so the smaller matrix, that determinant. So that is very useful in finding the inverse. Inverse of your matrix, where you're taking a matrix of your cofactors that you're calculating and multiplying by 1 over your determinant. And the way you can think about that is, well, when we're looking at a inverse where A is 2 by 2, you take 1 over the determinant of A, and then you multiply that by dA, and then we flip these to negatives. And the way you can think about that is, well, so what for the main diagonal, that means that the parity is going to be even. So we're going to have we're not going to change our signs, and then for our off the main diagonal, the sign is going to change, and then our cofactor our cofactors for our submatrices are going to be like so. Alright, so using this, find the inverse of this matrix. So pause the video, try that out. We need 1 over the determinant times our matrix of cofactors. This is going to be a lot, so get something to write with and start doing it. Okay, so we have cofactors, which we're going to have with our subscripts, and that's going to be, for 1, 1, we have positive, and then our determinant of negative 1, 1 for negative 2. And what's that? That's negative 2. And then our C1, 2 is going to be, negative, and then our determinant of 1, 1, 1, negative 2, and that's going to give us 3. And then, maybe I should zoom out a little bit, so we can say organized. And then C1, 3 is going to be positive again, and our determinant of 1, negative 1, 1, and 4, which is 5. And then I will not bore you with writing these out, but here we go. Cofactors for the next row, we're going to get 14, negative 7, and negative 7. So I have 4, negative 1, positive 1, negative 2, minus 1, negative 3. So we can collect these into our adjugate, and so we're going to actually transpose all of these, so we get the adjugate is negative 2, negative 7, negative 3, and then we do 5, 4, this is 3, and 14, and negative 7, and 1. I did flipping this way. Okay, so now we have our adjugate, and then what do we need to do? We need to figure out what our determinant is. How are we going to do that? So we could just do it using our cofactors and stuff, but we could also check to see if we got our correct answer for our adjugate, and we can figure out what our determinant is. And how can we do that? Well, if we take our adjugate, so we take the adjugate and multiply it by our matrix A, our original matrix A, then we should end up with our determinant times our identity matrix. So set that up, and then we'll see if we get it. So that's what we need to move this. Is equal to 14, 0, 0, 0, 14, 0, and 0, 0, 14. So this ends up with 14 times our identity matrix, 3 by 3 identity matrix. And so we have our, so confirmed, nice, we got our correct adjugate, and we also have our determinant, which is 14. So our inverse is 1 over 14 times, what do we have? Let me copy this. Times this, and I guess we can multiply that out so that we end up with negative 1 over 7, 1, 2 over 7, 3 over 14, that's nice, I guess, negative 1/2, and 1 over 14, and 5 over 14, negative 1/2 again, which makes sense, and negative 3 over 7. Boom. All right. Speaking about flops, so this theorem, which is our different way of finding our inverse, it's very useful for theoretical calculations. So it lets you like figure out properties without actually figuring out what the inverse is. But our AI with row reduction to get you IA inverse is a better way to actually find the inverse if you're actually looking for the inverse. But it is helpful to use Cramer's rule as like a tool for figuring out like how if you do tweak B, or if you like make perturbations, you tweak what A is, because of error, because for whatever reason, that you can figure out like how stable the solution is or how sensitive it is to those changes. So when you're looking at calculating your actual A inverse, Cramer's rule isn't super helpful, but figuring out what is still going on with the system, you can do some of that analysis using Cramer's rule. More things, geometry things. So if you have a 2 by 2 matrix A, then and it's made up of 2 different column vectors, A1 and A2, then the area of the parallelogram that you're getting from the matrix A is equal to your determinant. So the area here is equal to your determinant of A. And if you're looking at a 3 by 3, then the volume of the parallel pipette, which is taking a parallelogram and extruding it into R3, so you get this kind of thing. The volume of this parallel pipette you can find by taking the determinant of the matrix A that has the columns, which are vectors in your matrix. So this determinant is equal to the volume of this parallel pipette. Also, parallel pipette is really fun to say. Just parallel pipette, try to say it 5 times fast. I will try. It's going to be really bad. Parallel pipette, parallel pipette, parallel pipette, parallel pipette, parallel pipette. Yeah, that was really hard. So, that's fun. So, can you try to calculate the area of the parallelogram defined by these points, which you can see here, negative 2, 2, 0, 3, 4, negative 1, and 6, 4. And, we can take this parallelogram and translate it, and it doesn't change the area. Does that make sense? So, what is our matrix that we are looking at? We're looking at the matrix, what is this, 2, 5, and 6, 1, I think. So from negative 2, 2 to 0, 3, yeah, that's 2, 5, and from negative 2, 2 to 4, negative 1, that's 6, 1. Alright, cool. So the area of this parallelogram is going to be, what, 2 minus 30, which is negative 28. Oh, but it's an area, so we also need to take the absolute value of our determinant, so we get this absolute value of this number, and we get 28. So, if you have a linear transformation with a 2 by 2, so you're looking at R2, and you have a parallelogram S, then your transformation is looking at the transformation that you get from T on S is going to be equal to your area of your S times the area of the parallelogram defined by your transformation. So it's like scaling the area of what you have already. And that makes sense, right? And the same thing works with your parallel pipette volume, and the volume of your S, which is your parallel pipette in R3, where your transformation is going to scale the volume of your original thing by the area, or the volume, sorry, of the parallel pipette determined by your linear transformation. So that works with finite areas. So when you have something that you can take a finer and finer like mesh grid of, you can figure out your areas. But when you have infinite stuff, it's yeah. But that's nice for looking at areas of ellipses, which we'll look at next. So if you're if you're thinking about a unit circle, and then linear transformation on that unit circle can give you an ellipse. How do you find the volume of that ellipse? You could use the things from geometry that you either remember or you look up every time, which is totally fine. Or you could think about it with linear transformations and linear algebra. So let's look at this problem, see how we do. If you have positive numbers A and B, and you're looking for your area of that's bounded by this ellipse, how are you going to do that? Thinking about linear algebra. So we have matrix A that is going to give us our transformation, and this transformation is happening with a vertical and a horizontal transformation. We're not like rotating our circle, but we are stretching it, and or compressing it, depending on if A and B are greater or less than 1. And then if we have, if we just suppose that we have vector u and vector v as what we're transforming, then we also have that u is going to be, so if we have this, let's establish this better, that we have u is going to give us x. Then we also have that u is going to be u1 is x1 over a, and u2 is going to be x2 over b. And then from our unit disk, we can say that the area of our ellipse, so area is going to be equal to our determinant of A, the absolute value of that, times the area of our unit disk, D. And that's going to be, what, AB minus 0, 0. Times, and then what's the area of our unit disk? Pi r squared, but r is 1, so that's just pi. So the area of the region bounded by our ellipse here is going to be AB times pi, or I guess if we want to put pi in front, pi AB. Alright, so what did we learn? We learned that you can find areas of things using linear transformations to your advantage, especially when your transformation matrix has a really easy determinant. It's very, very straightforward, but you're basically scaling using your linear transformation matrix's area or volume, depending on if you're an R2 or R3, on your original area or volume. We can figure out areas of parallelograms using our determinants. We can find volumes of parallel pipets using our determinants as well. We can use Cramer's rule. It's a little computation heavy, so it's not necessarily the most efficient, aka hopelessly inefficient, but we can calculate, it is possible to calculate the inverse of a larger matrix, not just using our algorithm of augmented matrix with the identity matrix and then doing some row reduction. We can also take 1 over the determinant and then multiply the adjugate with our matrix of cofactors that gets transposed. We can use Cramer's rule to solve stuff, which is nice, and when we are using Cramer's rule to solve things, we need to figure out the determinant of our matrices that have particular column vectors replaced by our solution B, or our result B, to give us our solution X's. Alright. Wow, this is long. Whoops. Bye.